Bringing the Milky Way home. This is a title, but it's actually an aspiration, and we're trying to make the point that it's an achievable aspiration. If we can just get our heads straight, us meaning the dark sky movement broadly, about what works, what is effective, and what is needed to make the sky darker. It is actually achievable, but not if we continue doing what we've been doing broadly. You know there is bad news. I've been saying this for a while. Fabio Falchi did the World Atlas of the Artificial Night Sky Brightness, the second World Atlas, based on 2014 data and published in 2016, that showed about 78% of people living in the US live in places where they cannot see the Milky Way. In this map, based on that atlas, that's every place that is red, pink, or white. But it's not just, that was 2016. That's now nearly 10 years ago. But when this article was published, it appeared around the world in many newspapers. I think the New York Times, National Geographic, it appeared in a lot of places. But since then, the news in the last few years has become worse. People are beginning to make observations from the ground, which are useful in actually tracking the visibility of stars rather than predicting the visibility, which is what that atlas did. And the news is bad. Not only is it worse than we thought it was, because the actual visibility of stars is somewhat different than what's predicted based on those models. And I won't go into the details of why they're limited, the models. But also because we're adding more light and we're changing the spectrum of the light. But we know it can be better. Just by the observations, and probably I know all of you have seen this, the measurement that compared Flagstaff to Cheyenne, Wyoming, by National Park Service personnel using their night sky camera. Flagstaff and Cheyenne are almost exactly the same size. The observation points were almost exactly the same distance from the cities. And in fact, the city and of Cheyenne is a little bit smaller, and the observation is from a little bit farther away, both of which worked in Cheyenne's favor for making it fainter. But in fact, Cheyenne is a lot brighter. And the integration of the brightness of that light dome over the center of each image, the top one Flagstaff, the bottom one Cheyenne. If we call the bottom one a unit of 100 or 100%, Flagstaff is only 8.4% as bright. We know it can be better. This is something that has been on our webpage for at least 10 years, showing the quantified benefits, one of my specialties, of 3 important strategies in reducing light pollution. Reducing the amount of light, in other words, reducing overlighting, shielding light fixtures so that light only goes downward and not upward, and finally using amber spectra rather than white spectra. Those 3 give those respective benefits there: 25% for amount improvements or reductions, 50% for shielding, and 70% for spectrum. Together, if you did all 3 of those add together or multiply together technically to give you a 90% reduction. Interestingly enough, that's almost exactly what was measured in this measurement here. So, what would happen, this is what we're going to explore mostly tonight, if the rest of the world would pay attention to what we're doing and learn our lesson. First, what I'm going to do is go back to this map of 2014, and then I'm going to update it for 2023 data. That's the most recent data available from the satellite. It still has the same limitations of prediction of brightness that the old atlases do, but let's be consistent in the way we model these, and we'll use the models based on the satellite measurements. So 2014, and then we update it for 2023. And what I'll draw your attention to is the dark spaces in the west, and also the area around Mexico City near the label Falchi. Watch those 2 areas when we update the map. You can see that the dark places are shrinking. And I don't know what's going on in poor Mexico. Now, to predict what might happen if we applied two of the three strategies that I just detailed, not adjusting the amount of light at all, but just shielding lights and changing the spectrum of the majority of lighting, we're going to see how much better this map can get. So first of all, we're going to assume that this map is based on average lighting. Research shows that typically we have poor shielding, about 10 to 15% light goes directly up. And typically we're using a fair amount of white lighting. We're not assuming that it's all white lighting, but about 80% of the lighting is white. So now we're going to change these. First, we're going to improve the shielding. You'll notice that the map improves significantly. In fact, that is better than a 10-year improvement in the way we've been observing the growth of light pollution from the satellites. So we're backing up the clock 10 years just by shielding lights. But watch what happens when we change white lighting, nowadays LED lighting, to a mild version of amber. Not as strong as Flagstaff goes, but a mild version of amber, so-called phosphor-converted amber. These maps are based on calculations using a simplified model, which is the same, gives the same results as that producing the 2016 Second World Atlas that we started with. So, but we should have known this. Even when I saw that image of Flagstaff compared to Cheyenne, the data observation was taken in 2016, and it was published or presented at the American Astronomical Society meeting in January of 2017. I was stunned, but I shouldn't have been. These results here, which I just showed you, that they give a prediction very similar to what we measured, but these are not new results. These are published in 2009, 1986, and 2014. So these are 11 years old and older. I want to draw your particular attention, however, to the most serious deficiency in the way we're approaching light pollution control, and that is the spectrum. Amber lighting, as you can see from that image, gives the largest reduction of any of these strategies by far. 70%, according to this calculation, and borne out by the observations, apparently. But that's not what we're hearing. We're hearing that low color temperature white lighting, like 3000 Kelvin or 2700 Kelvin, is going to help us protect and restore our skies. If you look at the messages promulgated by the dark sky organizations that have credibility around the world, particularly Dark Sky International, you will see guidance that says 3000 Kelvin will help protect your skies, and their website says in quite a few places that their mission is to restore skies. So what am I saying when I say that that's not good? This is like gobsmacking. We're saying something completely different than what others are saying. And why are we saying this? So the first thing for all my physicist friends here, and there's a couple of us here, it has very little to do with scattering of white light or blue light. This is a little pet peeve of mine, and I hope you'll forgive me for harping on it a little bit. All my physics friends, they love to use the word Rayleigh scattering, and they drop it constantly, even after I tell them that that's not what it is. So looking at that 2014 paper, what we're going to look at here is the relative brightness of skyglow caused by several different types of lights here. We have the blue line on the bottom is a cool white LED, 5100 Kelvin. If you saw one of those, you would notice it's a blue or white. It's very common under service station canopies. It's not that rare. 4000 Kelvin, 4100 Kelvin is the violet line or the purple line. Ignore the FLED. That was a particular topic of the discussion 14 years ago that's no longer really relevant. Then there's the lowest color temperature LED that I commonly saw 10 years ago, which was the 2400 Kelvin. They're somewhat lower now. And then finally, the legacy amber light sources, high pressure sodium and low pressure sodium. What these lines show is how bright these light sources contribute, how much sky glow or sky brightness, artificial sky brightness, these light sources contribute relative to the gold standard of low pressure sodium. So what this does by taking that ratio is low pressure sodium always shows up as 1 all the way across the graph, all the way from 0 kilometers on the left side of the graph to 300 kilometers away on the right side. But this has removed the dramatic distance effect, and I'm intentionally removing that. The brightness falls off dramatically with distance, but the ratio is important for us. We're interested to see how much it has improved at any distance if you use lower impact light sources. So you can see here, for example, that the 4000 Kelvin white LED, actually it was a metal halide example there, but you can expect the metal LED would be about the same. Starts out at about 1.05 times as bright as low pressure sodium when you're right next to it, 0 kilometers away. And it falls below 1 and finally at about 10 kilometers and goes down to about 0.87 or so at 300 kilometers. So the important thing for my physicist friends to notice here, first off, is that the brightness caused by extra blue in the spectrum and the Rayleigh scattering that we think is going to kill us because Rayleigh scattering is proportional to the inverse wavelength to the 4th power. That's enormous, isn't it? Well, it's less than a 10% effect, even next door to the light. And in fact, if you get more than 10 kilometers away from the light, the blue light sources are fainter than the yellow light sources. It's not Rayleigh scattering that's causing this. So what is it? What's going on here? We have to detour away from physics and go into biology, a much wetter subject. So it has to do with the eyeball, and I'm going to skip over that. We know the eyeball has a lens that focuses light onto the back of the eye where the retinal photosensitive cells are. Those cells are of 2 types, rods and cones. They don't generally operate at the same time. The cones operate in the daytime and in lighted environments like our houses and roadways, parking lots, driving, etc. And then the rods are night vision and operate when we're looking at unilluminated nighttime environments below moonlight, looking at the night sky in particular. So these 2 light cells, photosensitive cells, or groups of photosensitive cells, rods and cones, have different spectral sensitivities. That means that they're sensitive to different wavelengths, to the wavelengths of light in different ways. The daytime vision is most sensitive to the yellow-green portion of the spectrum. It gives us color vision. Its peak is at about 550 nanometers or 555 nanometers. However, our dark adapted vision is not color vision. It's only black and white, but it's much more sensitive, shifted toward the blue. It peaks around 500 nanometers and is what we use when we look at the night sky. So I want to convince people that looking at the night sky is indeed scotopic, and our lighted environments are not scotopic. The lighting industry particularly needs to hear this, and none of you do, but I'll skip quickly. Our office lighting environments, what I'm looking at here across the bottom is a range of brightnesses. It's called luminance in technical units, and I've got a logarithmic range across the bottom, which goes from 1/10,000th of a candle per square meter to 100, a range of 1,000,000 to 1 left to right. So on the left, it's very dark, and on the right, it's fairly bright. It gets brighter than that if you're like out in the snow, but our office lighting falls on the right side of that. So indeed, we are photopic and how the eye responds to bright light is absolutely relevant for that. Street lighting begins to get into the area called mesopic, where the rods are starting to function a little bit, but only a little bit. It's much closer to photopic, and its spectral response is, you still have color vision, for example, when you're driving down a roadway at night, and you can see the stripes on the road, you can see the colors of cars, etc. Full moonlight is getting to the lower end of mesopic, but still 10 times above the range where you need to get to be purely scotopic and looking at the night sky. And this is where the night sky falls, even in urban areas. I wonder if Phil has made measurements in his where he lives with an SQM, and I bet if he has, he gets numbers which are fainter than 18th. Am I right, Phil?
In my driveway, looking up, it was 20.8.
So, and Phil is in, well, he's not directly in Charlottesville, he's a ways out.
About 30, at least 30 miles from downtown.
Oh, well, you're farther than I remembered, Phil.
Yeah, well, I didn't live there before. I live here now.
Right.
Most of our bright lighting are shopping centers from Charlottesville going north. So I'm sort of, I don't know if you want to, some of the area lighted waiting is farther away for me than.
Well, so you're in a dark area.
Yeah.
You're somewhere here in the middle of this purple range, quite scotopic, if you're looking at the night sky. Now, if you're looking at your porch or you're looking at the light of the road, the roadway illuminated by your headlights, you're back up here in this street lighting area. But if you're looking at the sky, you are here, well comfortably in dark adapted vision. I have had measurements made. Flagstaff at City Hall is fainter than 18th. It's about 19 or 19.2. It's right about here. I have had measurements made around Tempe, Arizona, which is in the heart of the metropolitan Phoenix area, a population of approximately 5 million people. And they have typically measurements between 18.0 and 18.6. Once you are away from the heavy commercial districts and in the residential areas. So even in a large urban area, we are dark adapted. So going back to this graph, that means that the scotopic vision is what is important, not photopic. Oops, I had more slides in here than I thought. Let me zip through them. So when we are looking at designing lighting, we're using the photopic measurement. That's where lumens are defined. That's where foot candles are defined. That's where candela, all the units measuring the visible sensation of light are based on that photopic curve. That does not apply very well to looking at the night sky. That is scotopic. Now they do overlap, but it's a significant difference, particularly when we talk about the different kinds of light we use for illuminating our environment at night. This is the part of the spectrum we can see. The spectrum goes from red to violet, but the scotopic vision can really not see the red. It's most sensitive to blue-green, not yellow-green like photopic, but blue-green. Here's an important point to make. People keep talking about the blue light being what's killing us. It's clearly the blue and the green, in equal proportion, almost exactly. And we don't see color if we're looking at the night sky. If your sky is really bright, you're looking down near the horizon, you might be able to start picking up some color, but that's when it's brighter than 18th magnitude. So, looking at these sampling of light fixtures, we're showing their spectra. At the bottom, we've got an LED, which is a broad spectrum source. It emits all colors of the rainbow except
sky.
Excuse me?
Sorry.
Oh, okay. It has a deficiency kind of in the deep blue, but violet and royal blue, and then the green, gangbusters in green, and yellow and orange and red. A metal halide, which is commonly still used somewhat in sports lighting and some service station canopies, it's becoming obsolete. High pressure sodium is very heavily weighted towards the amber part of the spectrum. That's the part that the scotopic vision has very little sensitivity to, even though our night vision looking at a roadway can still see it quite well. There's an amber LED in there, which is also like the high pressure sodium, except doesn't have any blue light at all. Like the high pressure sodium has this blue line here, but amber LED does not. And finally, low pressure sodium, which is the old legacy gold standard, has a spectrum which is almost invisible to night vision. So, if it's not Rayleigh scattering, what is it? It's scotopic vision. And our sensitivity, our dramatically increased sensitivity to blue and green light. So these curves here that I showed to you before, ratioing the impact on sky glow of these different spectra compared to the gold standard of low pressure sodium, it could have been amber, narrow spectrum amber LED or high pressure sodium, almost the same answer, is really a photopic sky brightness versus distance. But we're not looking at using photopic vision looking at the night sky. So let's fix that. Let me skip that slide. What I do here is, for each of these curves, I move them upward based on their ratio of scotopic to photopic brightness. So the bluest ones have more scotopic brightness, more brightness to the dark adapted eye. The yellow ones have less. So the ones that are lowest down on the right side of the graph are going to move up, and they move up significantly. They are the same shapes as you saw previously, but moved upward by that amount just to correct for the sensitivity of the eye to blue and green light when looking at the night sky. Now we see where the problem lies. When you're nearby, if you're comparing it to low pressure sodium or high pressure sodium, which are 1 or 2 in terms of their brightness, low pressure sodium is definition 1, and high pressure sodium is about twice as bright when you're nearby. You can look at the metal halide or the 2400 Kelvin LED, which is the yellow or orange line there, which is barely distinguishable from the green one. And you can see when you're nearby, it's 3.5 to 4 times as bright. That's the culprit. 3000 Kelvin CCT, which is commonly recommended in the dark sky business, is worse than that. It is 5.4 times as bad as a good amber source when nearby. I'm going to skip these 4 graphs because they were presented elsewhere, and I'm not going to cover that here tonight. I'm going to go back to our Atlas of 2023 and show that we really can bring the Milky Way home and show what the impacts will be on the people who live in North America, or actually in the United States, if we did what we talked about switching just to full shielding and amber lighting. As we said before, the Milky Way is invisible to more than 78% of the people in 2016 or 2014, and that's gotten worse. So it's greater than 78% now. If we switched it to amber lighting and shielding, and we have not changed the amount of light in photopic measurements on the ground at all. We have not addressed overlighting. We have not lowered the foot candles. We have only changed the majority of outdoor lighting, such as roadways and parking lots, but not outdoor eating areas or sports fields. Those are all white still. We've changed the others to amber, and we've shielded them. Now the Milky Way is invisible to only 24% of the people. That conservatively estimated, following Flagstaff's example, about 3/4 of the US population, 265 million people, could see the Milky Way where they live, whereas today less than 80 million people can see the Milky Way where they live. This restores visibility for almost 190 million people, And further, a critical aspect of this is that if we can use this word nowadays, it restores equity to the night sky. The people who can travel to dark places on the map, take vacation, have the resources to travel there, have the time for vacation, that's not everybody. If you do it where you live, it doesn't matter whether you live in a trailer or in a mansion. It doesn't even matter if you live under a bridge. You can see the Milky Way if you restore the visibility of the Milky Way in our urban areas. This is not a pie in the sky story. So I wanted to bring us back to that and entertain any questions. This is something that if we can get our dark sky advocacy on point better and get the message out that is well supported by science and measurement and theory, then we can actually realistically restore the night sky. So thanks for your time, and I'll stop sharing the screen, or maybe I'll leave it sharing in case there's any. I'll stop it and we can go back to it if anybody has questions. Everybody,
You can just about see Charlottesville on your all of those U.S. maps. There's quite a dark area.
Oh, Phil froze. Phil, if you can still hear us, you've frozen and we can't hear you. At least I can't. Anybody else?
That matters very much, but we could easily be much better if people would do things right. Charlottesville just adopted a new lighting ordinance about a year ago. And one of the things they have in there is they require a CRI of 80.
Yep.
And that's the architects.
Yeah, it's
on the board that did that.
Speaking amongst ourselves here, even though this may go on YouTube, and if somebody sees it on YouTube, they may want to get angry about what I'm going to say.
No.
But it's based on junk science, Phil. It's based on this idea that people are safer when they can have color rendition, or if they are called on that, they often say, well, people just want it. They want to be able to see accurate color. None of those are documented.
It's also part of the question of architects' taste in things. They like color vision better than amber vision. And I think an argument against that is against nature. We evolved quite happily with bright sunny days and no artificial light at night at all. And our metabolism, the way our whole body works, is in sync with that behavior.
Or if we had light at night for thousands and thousands of years, it was probably just firelight.
Firelight, yeah.
Yep.
Yeah. Which is a good amber color.
Yeah, amber color. So I would say I don't want to diminish other concerns about lighting. And color rendition is an issue, and people can think about it and have different opinions about it. But I don't think the facts about the damage of non-amber light are being adequately laid out, nor are the advantages of it being adequately laid out. And I think if they are carefully laid out, that the balancing of the pros and cons might go another way than it usually does.
Something about the 3000K lighting is sort of the standard. I mean, locally, the ordinance says nothing above 3000K because they were looking for something that was a little more mellow than white, harsh lighting. But one of the problems with that is 3000K is not at all a way to estimate the amount of blue light in anything. You can find, I found a paper not long ago that shows the spectral power distributions for 5 or 6 different LEDs, all rated at 3000 K. The amount of blue light varies from, I don't know, maybe 15% to 25%.
Right.
But if you choose something by 3000 K and you're worried about the harm of blue light,
right. That underscores the point I've been trying to make, is that color temperature is a wrong metric to use when we're talking about night vision. Color temperature is completely focused around color vision, which is photopic vision, which is irrelevant to the night sky. So everybody thinks we're going to address it by percent blue or color temperature. Get away from that stuff. Start talking about the brightness of scotopic to photopic vision. People talk to me and say, oh, but that's so weird. Nobody likes that. You know what? IES was all over it 10 years ago when they were thinking they could use it to give advantages to metal halide lighting.
Yeah.
The IES Lighting Handbook 10th edition had a scotopic to photopic ratio and mesopic correction factors, which they were using to say, hey, look, this white lighting, you can lower the brightness a little bit because it's so much better at stimulating night vision. But now they pretend that it's this really esoteric, difficult thing to calculate. No, it isn't. It's easy to do. And the dark sky people really should be making that point. The industry they're not vision experts. They're mostly, as you know, Phil, the lighting people it's a trade organization. They sell products and services. There is some science behind it, but not much.
There are a few people who are vision people, and I've seen elsewhere a couple of times anyway. It's stated that you can't use color temperature as a way to judge the quality of light. So
nor CRI. You know what CRI is?
Nor CRI. Yeah.
CRI is a kludged metric that takes like 15 or 20 different wavelengths and says how accurately can you match those to their visibility under incandescent light or their color under incandescent light. And you can get really good numbers on 15 of them and get horrible numbers on the others, and it still comes out CRI 75 or 80.
Yeah. Nancy Clanton once years ago had put a couple of light boxes up to demonstrate the differences from different manufacturers of the same CRI. So she had light sources of whatever the CRI was, lighting up this sort of little dollhouse, and another one right next to it, the same CRI. And the colors were very distinctly different. No question.
Which is a fun and cute demonstration to make. At Light Fair, I saw many of them, and you did too, probably, Phil, where they would have tomatoes, vegetables, and the tomatoes look gray under one light and brilliant red under another. And it's all cute and it's kind of clever, but it's all irrelevant to the night sky.
Well, maybe the application gets people think a little bit more and broaden their view of what they're doing in the night sky as well.
Well, vision is a fascinating thing. How the eye works in day and in night is all fascinating, and there's 1,000 different things to different rabbit holes to go down, if you want to call it that, and it's a lot of fun. But I think our dark sky advocacy needs to focus more on the science of protecting the night and stop worrying so much about the quote unquote science of lighting design. Let them worry about that. We need to speak up for the night clearly. And I don't think that's happening as broadly as it needs to. And the results of not speaking up clearly are before our very eyes in the last 10 years. It is becoming clear that despite 40 plus years of effort of the dark sky organizations, the night is getting worse. And it's not getting a little worse, it's getting a lot worse. At the same time that we're claiming that we're making it better, we're providing good guidance, we're restoring, we're not. Apart from Flagstaff, I haven't seen an example which shows that there's been a dramatic improvement anywhere.
There's a great deal of ignorance about nighttime lighting. And one of the things I did years ago was I took some of our county government staff, supervisors and planning people out and just looked at lighting and tried to illustrate directly that what is good lighting and what is bad lighting. People think, and it's in their locked in their brains, that nighttime shopping center lighting is bright, white, and glary, and without knowing that it doesn't have to be that way.
Right.
And that sold the local lighting ordinance, I think, very much so. When people finally, and there were architects along in these tours who were planners in the county, and they said, well, they had never really looked at nighttime lighting that way.
Right.
So opened their eyes or something.
Yeah, well, that reminds me of the other thing we constantly bring up, and that is all the brass and glass fixtures that are sold to the residential market. Clearly, the people who designed those never observed or certainly didn't think about what they look like at night, because they're horrible. They're horrible for vision. They obscure your vision. They don't improve it. But that's more than 90% of the lighting in the residential market. Walk around your neighborhood, and that's almost all you see. And it's as obvious as day when you show somebody it, that a shielded light gives visibility and doesn't cause trespass. And an unshielded one may look great in the showroom or in the daytime, but it gives horrible lighting. But boy, as obvious as that is, it's remarkable how little penetration that has had.
Yeah, it's that one of the things I remember Dave Crawford always was talking about, and it's true, is very often people choose fixtures by how they look in the daytime and not their performance at night.
Right.
Form over function. And that seems quite a common mistake that, hard to fix. But, here's educational opportunities here to try to enlighten or something.
Yeah. Yeah, it's a perennial problem, and not just in dark skies. And that is reestablishing people's awareness of and connection to the environment that they live in. They're not aware of simple things like glare decreasing visibility and light fixtures that aren't shielded causing glare, not because it isn't obvious, but because they're so isolated from that particular aspect of their environment, as they are for many other aspects of their environment. It's a challenge. I don't think that what I've shown tonight about improving skies and the Milky Way being accessible for most people is going to change the difficult political problems and economic problems communities face, such as you have been butting your head against for your career, Phil. But one of the things that we often lament is that why aren't more people pushing to make it better? Or why are they settling for 3,000 Kelvin or a little bit better when they ultimately are settling for skies that are getting worse? And what I think that this message can do is if it can make clear that much more is realistically attainable and has been proven on the ground for more than 30 years in Flagstaff. Crime has not gone up. The economy has not collapsed. Pedestrians are not getting run over. It is people can find their cars in the parking lot at night. And that is, we're not just a town of 4,000, we're a town of nearly 80,000. I think that's a substantial point that I think can help people around the world say that we can do better. And if we think they can do better, they might try harder.